Howdy, I'm Miranda Lobermeyer, and I'm a rising junior at St. Norbert College in Wisconsin. This summer, I've been working in Dr. Blumel's research group, and today I'll be talking about palladium catalysts immobilized on silica. Catalysis is immensely important in academia and industry. Some transition metal catalysts are expensive or require sophisticated syntheses. Immobilized catalysts are a possible solution for this, as they offer the benefits of traditional heterogeneous and homogeneous catalysts. Bound to an insoluble support, these immobilized catalysts can be easily removed from reaction mixtures and recycled, while remaining highly selective. Immobilized Sonogashira catalysts in the past consisted of separate palladium and copper components. By bringing these metal centers closer together as a heterobimetallic complex, this system may be improved. Radical-initiated hydrophosphonation has been determined to be the most effective pathway to synthesize ligand 1. From here, this ethoxysilane ligand can be immobilized onto a silica surface, forming the functionalized silica of 1I, continuing to form 5I when combined with a palladium source. From ligand 2, an air-stable borane adduct can be formed as well as the palladium complex 4. A powerful technique used to characterize surface-modified silica is solid-state NMR spectroscopy. High-resolution magic angle spinning, or HR-MAS, involves functionalized silica packed into a rotor with a drop of solvent. The solvent acts as a means for some mobility within the covalently bound species, which allows for shorter relaxation delays, shorter measurement times, and higher resolution. Cross-polarization magic angle spinning, or CP-MAS, allows magnetization to transfer from easily polarized nuclei to nuclei that are less abundant, less receptive, or spatially close and desirable. With immobilization of disiloxanes, the silica used was either dried in vacuo at room temperature or rigorously dried in vacuo at 300 degrees Celsius. Hexamethyl disiloxane and hexaphenyl disiloxane were added in an amount to form a monolayer. The 29 silica NMR spectra of the disiloxanes immobilized on room temperature dried silica showed no measurable signals. However, hexamethyl disiloxane on the rigorously dried silica yielded 6I, while hexaphenyl disiloxane remained crystalline and did not react with the surface. The changes within the chemical shift at signal half-width on these NMR spectra indicate that 1I is covalently bound to the surface. Regarding the palladium complexes 4 and 5I, the change in chemical shift may be due to a trans to cis coordination change. Figure 7 suggests degradation of 1I, forming 8I. Additionally, HR-MAS produces sharper peaks compared to magic angle spinning alone, where no solvent is present. With surface mobility of palladium, the tripodal linker allows for the palladium mobility on the surface to both occur in solution and in the presence of uncoordinated phosphine groups. This palladium mobility on the surface is shown by the broad signal in the HR-MAS spectrum. As shown in Figure 9, the palladium can hop between different phosphines on the same surface of silica, but the possibility of palladium moving between different surfaces is still in question. As far as future work goes, the possibility of intermolecular palladium hopping on the surface and the effects various solvents have on this palladium mobility will be investigated. The mobilization of both hexa and butyl disiloxane and the disiloxane congener of ligand 1 will be attempted. Additional homogeneous and immobilized Sonogashira catalysts will be synthesized, and catalytic activity will be compared to other catalyst systems. The formation of palladium or mixed palladium and copper nanoparticles will be investigated after catalytic runs. This work was supported by the National Science Foundation. Thanks so much for watching.